Hi, I'm Coach Cowland. In this presentation, we're going to look at mechanical energy. So there are three forms of energy that we look at when we talk about mechanical energy. We look at kinetic energy, elastic potential energy, and gravitational potential energy. And we'll look at each of those in turn, and we'll look at the mathematical equations for each of them as well. So we talked about open systems and we talked about closed systems. And when we have ideal mechanical energy closed systems, we have no friction. The reason why this is significant is because friction causes heat generation, and that means that if heat is generated, it means that that heat energy is coming from the mechanical energy, which would mean that the mechanical energy is decreasing as the heat energy is being generated. So we end up with a constant decrease of mechanical energy. Even though the energy has been conserved, it is not efficient because the energy is not useful. So if in an ideal closed system, say you have something like a pendulum, it would keep on going forever. Um, if there is friction, then the amount of mechanical energy that you have will gradually decrease. Now, when we talk about mechanical energy systems, generally what happens is that the energy switches from one form to another back again. Kind of like the analogy with the money, except for we're limiting the different forms that the energy can take from the three that we've mentioned: kinetic, potential energy, elastic, potential energy, gravitational. So here is the mechanical energy equation. The sum of your mechanical energy is equal to your kinetic energy plus however much elastic potential energy you have plus however much gravitational potential energy you have. Pretty straightforward, right? So if there's no friction, the amount of mechanical energy that you start with is the same as the amount of mechanical energy that you end with. If there is friction, it's a little bit more complicated. The amount of mechanical energy that you start with is equal to the heat from friction plus however much mechanical energy that you end with. This means that ultimately you will always end up with less mechanical energy at the end than you began with. Friction will never give you more energy in. It will never do more work for your system. Again, I've brought up work, and we will come to what the work is in terms of physics and motion a little bit later down the line. So let's look at the first of these forms of energy, kinetic energy. Kinetic energy, kinetic means moving and motion, and it is the form of energy that anything that is moving has. Anything that is in motion has kinetic energy, and it is dependent on two variables: mass and velocity. If you increase both of these things, you increase the amount of kinetic energy something has. So the equation for kinetic energy is equal to 1/2 mass times the velocity squared. Ke equals 1/2 mv squared. This is on your AP sheet, but you should definitely make a note of it. Potential energy. When energy is stored, as we said, it's called potential energy. This is kind of storing energy for use later. And there's two kinds that we can look at. We can look at gravitational potential energy and elastic potential energy. So let's look first at gravitational potential energy. Gravitational potential energy is energy that's stored because you're doing work against the force of gravity. How do I know that I'm doing work against the force of gravity? Well, if you pick something up and then you let it go, what happens to it? I'm pretty sure that what's going to happen is it's going to drop, and it's going to get faster and faster and faster. Now if it's dropping, then it's moving, and if it's moving, it now has kinetic energy. But what's happening to its height as it's moving? It's decreasing. So as its kinetic energy is increasing, its gravitational potential energy is continually decreasing. Okay, you have lifted it up, so you've done work and you've basically put energy into it in the act of lifting it. And then what you've done is, once you've let it go, you've taken that energy and you've allowed it to change that energy into a useful form of energy and use it by making it go faster and faster and faster. And it's dependent on three things: how high it's been lifted, or how the change in height, the mass of the object, and the acceleration due to gravity. So if you lifted something up that's much heavier, you've done more work and then there's more energy. If you've lifted something much further, you've done more work and there's more energy. And if you are close to a black hole instead of close to the surface of the earth, the gravitational pull is much greater, so it's much more difficult to lift something up, and therefore it has a lot more energy and it will go a lot faster. So the equation for gravitational potential energy is also pretty straightforward. It is the product of the mass times the force of acceleration due to gravity, times the height, or the change of height, really. PE is equal to mgh. Now, don't get gravitational potential energy confused with elastic potential energy. They are very different, both mathematically and in what they mean. So elastic potential energy is the energy that is stored when something is stretched or compressed. When you compress something, you do work on it, which is the reason why when you release it, it will move, because again that stored energy is being transferred into kinetic energy and it's moving. So this energy is stored in the spring, and it's the energy that restores it back to its original length. Now, if you think about it, that how far it's stretched or compressed kind of has to be a part of that equation, because the more you compress a spring, the harder it is to compress. The more work you do, the more difficult it is, and the more you compress a spring, when you release it, the further it will go. The equation for elastic potential energy is 1/2 kx squared. Now k is a spring constant, and x is the amount, the length that you've stretched or compressed it from its natural position. Now these two variables are very important that you understand them. Each spring has its own spring constant. This is because not all springs are equal. If you get a spring from a car suspension, it's very, very difficult to compress it. If you get a spring from a pen, for example, it's very easy to compress it. Even if you compress them the same distance, you would have to put a lot more energy into and a lot more work into compressing the car spring than you would the pen spring, and therefore it makes more sense that it has more energy potential, more stored energy. And x is how far you've compressed it or how far you've stretched it from its original position. Now, all of the units that I've mentioned here, the masses, the acceleration due to gravity, the spring constant, the length, and that, they all need to be in SI units. So if you have a little spring and you compress it 4 centimeters, then when you plug this into the equation, you need to make sure that you plug in 0.04, because that is its length in meters. Okay, make sure that you always use SI units for these, otherwise your values will be way off. So here's an example. So we start off with a basketball, and on the ground it's when you throw it, it's going pretty fast, so it has a lot of kinetic energy. Now, if this is its starting position and its ending position, you could say its initial potential energy, gravitational, is 0. So all of its energy is kinetic. Now, at its midpoint, it started to slow down, but it is higher than it was, which means that its kinetic energy has decreased and its potential energy has increased. So this means that this change in gravitational potential energy is equal to the change in kinetic energy. One's decreased by a set amount and one's increased by a set amount. So say your kinetic energy was initially 10 and it's now 5. Your potential energy, which was 0, would also be now 5. And the sum of your mechanical energy would still be 10. Now, when your basketball gets to its highest point, it will slow down to a point where for an instant it will completely stop, and that will be the highest point it ever gets to. At that point, its kinetic energy is 0, then its potential energy is at the maximum that it can ever be, because its height is the greatest that it will ever be. Its mass hasn't changed, the acceleration due to gravity hasn't changed, so the only variable that has changed is the height. So you can conclude based on that that it's the gravitational potential energy at that point would be 10 if we started off with 10 joules of kinetic energy initially. That would also be the sum of the mechanical energy. Okay, thanks for watching.